Okay, so today we're going to define the relationship between free energy, cell potential, and electrical work. Basically what that means is we're looking at Gibbs free energy, our delta G, and we're relating that to our cell potentials, our E naught. That way we can look at whether or not something is spontaneous or non-spontaneous. Before we looked at everything under standard conditions. There was a reminder, our standard conditions is when we have a concentration of 1 molar, we have a pressure of 1 atmosphere, and we have a temperature of 298 K or 25 degrees Celsius, right? So we're looking at situations when that does not happen. So whether the pressure is changing, or if the concentration is changing, or if the temperature is changing. We're primarily looking at when the concentrations are changing today, but there are examples you could encounter where the temperature or pressure would change, and we have to look at the equilibrium of that. And since we're looking at equilibrium, we're also going to have to look at K constants, and so we will be able to calculate K, our equilibrium constant, for our voltaic cells. Remember that the third quest, which is standard reduction potentials, is due on Tuesday, the 3rd, and then the quest that is in relation to this lesson is due on the 10th. So hopefully this clears up some of the issues we've been having with the free response. And someone mentioned the other day that they were upset that I didn't have an intro in my play posits. So I am going to work on that. I will try and get an intro, but no intros for now, just because we are pressed for time. But I think that would be awesome to have an intro at some point. So thanks for the suggestion. Okay, cell potential, electrical work, and Gibbs free energy. So when we're talking about work, just in a basic sense, we know from past science classes that work is the force times the distance. In terms of chemistry, we're talking about chemical work, so energy transfer. When we're talking about energy, we're talking about joules. So the amount of energy that's being produced through the transfer of electrons through our wire. That is what we're talking about. That is dependent on the electromotive force. That is our EMF. We talked about EMF in the last lesson. That's our push in our circuit. It's what causes us to move from anode to cathode. And we already know that that's measured in volts. But for this lesson, even though we spent time measuring things in volts, we want to break down where that volt unit comes from. It comes from the work, which we measure in joules, and then the charge. The charge, we use a letter C. The unit is a coulomb. So a coulomb, we do have a specific number that we use for that, a constant. It's called Faraday's constant. I'll talk about that a little bit later. But whenever we see a coulomb, we use the letter C. So this unit of joules per coulomb is equal to our E, right? Or it's equal to the volts. So before, when we saw E being written with units of volts, for the purpose of what we're doing, we're going to use it with joules per coulomb, because it will make the units cancel out nicely when we're talking with delta G. So the reason that is because 1 joule of work is produced when 1 coulomb of charge is transferred between 2 points in our circuit. And that's why they set that equal to 1 volt. So that's our standard. So if work flows out of our cell, it is assigned a minus sign. So we want to think of endo versus exo, right? If we're an exothermic reaction, if we were thinking about things like delta H, we would have a negative delta H value because things are leaving, right? It's a product. We're getting rid of it. Whereas if it's an endothermic, in this case, if work energy was flowing in, then it would be a positive sign. But we are causing the energy to flow out, right? If it was a battery, the battery isn't going to absorb energy. That's pointless, right? We want the battery to give off energy. So we're producing power that we then can use to power other things, right? So the work is flowing out. So therefore, we're going to have a minus sign. So when a cell produces a current, we know the cell potential is going to be positive. because positive means it's spontaneous. When it's positive, that current can be used to do work. We're producing some amount of energy in joules, right? For that reason, our cell potential and our work are going to have opposite signs. So we have this relationship between our work and our charge, right? So the negative work value we get because we're giving off energy over our charge can be framed in terms of moles for our reaction. Right? When we're thinking about delta G has units of kilojoules per mole. So since we're talking about moles in our reaction, everything's proportional to the moles in our reaction, we're also going to have to put our charge in terms of moles of reaction. So the way we get around that is if we have our work over our value Q. Q here is the number of moles of electrons times F, which is our Faraday. The Faraday is the amount of charge on 1 mole of electrons. They use this unit Coulomb. So the official textbook value that you'll see a lot is 96,485 coulombs. And that's coulombs per mole. College Board likes to use 3 sig figs, and they round it to coulombs per mole of electron. So 96,500 coulombs per mole of electron. Okay. So if we're thinking about this in terms of units, we have negative W. We know W has a unit of joules. And then we have our cell potential, which we said is volts. Earlier we said volts has a unit of joules over coulomb. Joules over coulomb. And then we have this Q. So Q is our number of moles, the moles of electrons, times Faraday's constant, which has a unit of coulomb over mole of electron. When we multiply these things through, moles ends up canceling because they're on top and bottom. Coulombs ends up canceling because it's on top and bottom. And we're left with the joules. So the amount of joules that we make is the amount of joules that we give off. So the work is equal to the negative of that. So for that reason, that negative is really important for when we're talking about delta G, or Gibbs free energy. So let's see if we can remember. When is delta G spontaneous? When is delta G not spontaneous? Think about the signs. See if you remember. Delta G is negative when it is spontaneous, right? If you think back to the equation from last year, delta G is equal to delta H minus the temperature times the entropy. We will get back to this equation. You might see this on your formula sheet. But for delta G to be spontaneous, we need to have a negative delta G value, a negative kilojoules per mole, because we're producing that free energy that's available to do work. So, that being said, for a process carried out at constant temp and constant pressure, the maximum amount of work. Now, I wrote maximum amount of work, but we're neglecting, I would like to point out, we're neglecting the amount of energy that's lost as friction or heat in our wire as we are transferring electrical energy from one spot to the other. If we leave that part out, the maximum amount of work we can produce is going to be equal to delta G. It's a very valuable relationship. So if the work is going to be a negative value, work is negative, delta G is negative. Okay. So with that being said, we can now talk about our Gibbs free energy equation. we had that relationship before where we had the delta G is equal to delta H minus T delta S. With this, we're looking at the cell potential. We're going to need Faraday's constant and the number of moles, because those are all the things we said were equal to our amount of work being done. And sure enough, if we look here, we had our N, that was our number of moles, we had our Faraday's constant, and we had our E cell, right? So we actually just put this together, we just derived this equation. So N is the number of moles of electrons being transferred. So we're going to have to balance our half reactions when we see those half reactions. For example, I don't know, copper 2 plus and 2 electrons, and you get copper solid out of it. Those 2 electrons, that's your N, the number of moles that I'm talking about. So it would just be 2 electrons per mole. Faraday's constant has a unit of joules over volts times mole. That is what a coulomb is equal to. So we're going to just refer to it as a coulomb. So joule over volt times mole. So again, just a refresher, a negative cell potential means what? Non-spontaneous. Right? We spent all this time trying to make things positive, and the more positive it is, the more spontaneous it will be. Okay. We're going to use the table of standard reduction potentials and calculate delta G for our first reaction here. So we have copper 2 plus iron, and we're going to get copper solid and iron 2 plus. So we need our table of reduction potentials. So we need, where is it here? Looking for copper 2 plus. Copper 2 plus is right around here. That is got a cell potential of 0.34. And then the iron, iron is down here. That is a negative 0.44. So if we go back to our screen here, we've got our 2 half reactions. Remember, we want to write both of them as a reduction first, and then we flip. So we got Cu2 plus 2 electrons, and we get copper solid, and our E was 0.34 volts. Okay, and then we have the iron 2 plus 2 electrons, and we get Fe, and this is negative cell potential, negative 0.44 volts. Okay. So again, when we add these numbers together, we want to make it so that it is positive, so it's spontaneous. So we're going to look and see which of these is our reduction and which of these is our oxidation. So here we've got our 2 plus coming down to a solid, which means it's being reduced. Copper is our reduction in this reaction. And then that means that iron is being stripped of its 2 electrons, and it will be the oxidation reaction. So with our oxidation reaction, we're going to have to reverse. So I'm just going to put REV for reverse. So we get FES, Fe2 plus, 2 minus, and we've got our cell potentials in the right spot, 0.44 volts. And we can add together the ones that we need. So we're done with that reaction. We know our electrons are going to cancel. That's easy. We add it together. 0.78 volts is our E value. Now delta G, that's the easy part. Delta G is equal to negative, we have 2 moles of electrons, 2 moles of E. That becomes from the 2 moles that we transferred, right? We've got our Faraday constant, 96485 coulombs per mole of electrons. Coulombs per mole of electrons. and our E cell. Now remember that that volt unit is the same as joules per coulomb. And that's really important because when we multiply these things through, let's take a look at what happens to our units. Moles is on top, moles is on bottom, that cancel. We got coulomb and coulomb, that cancels. We should be left in joules. So let's go to our calculator. We've got, make sure it's on, negative, and in parentheses 2 times 96485. Again, if you wanted to use the 96,500, the rounded value, that's fine too. Your numbers might be a little off, but you should still get the same answer based on sig figs. 96485 times 0.78. Okay, and we get this huge number, negative 150,516.6 joules. With this, we should round to 2 sig figs. When we are looking at our numbers here, the 2 isn't going to be used to decide sig figs. That's just a quantifier from our balance equation, so we don't want to use that. And then constants, we usually don't consider constants in our sig figs. So we have 2 sig figs in our answer here. We get negative 150,000 if we're counting 2 sig figs, and that's joules. Remember that this is actually joules per mole. So it's joules per mole. And we also usually report delta G in kilojoules, so this is negative 150 kilojoules per mole. All right, and that is our delta G. Delta G equals. So then, I know I said before it is spontaneous because in this case it's a galvanic cell, but it won't always be, so it's good to confirm that your numbers tell you what it is going to be. So in this case it is negative 150. Negative delta G is going to be a spontaneous reaction. Well, actually, my fault. One thing I forgot, if we're looking at our units, we have 2 moles of electrons in this reaction per moles of reaction, so the moles of the entire reaction. So that's why we have the mole down here in our unit. This is the mole of reaction. That is my fault. Should have clarified that. Moles of reaction. So joules per mole of reaction that we have proceeding. Okay. So the delta G part's fairly easy. This is where it gets a little bit trickier. We're looking at how things behave in terms of concentration. Remember, standard, everything was 1 molar, so if the concentrations were the same, it's easy to figure out the flow. Here we really got to look at Le Chatelier's principle. So an increase in the concentration of reactant to review equilibrium. If we increase the reactant, tips our scale, it's going to move in the forward reaction. When that happens, we increase that concentration and we move in the forward direction, our cell potential will increase. The same is true of the reverse. If we increase products, it's going to tip our scale backwards and the reverse reaction will be favored, and then our cell potential will decrease in that instance. So I'm going to look at this problem here. This is in your NAMESY packet. This example we're going to do in 2 ways. First qualitatively and then quantitatively. So first is qualitative. I'll look at this qualitatively, which means we don't actually have to do much math. We just have to think about our initial conditions versus our new conditions. So the initial is at standard. We would assume for initial, because we have an E cell, which means standard conditions, we'd assume we're starting with 1 molar manganese 2+, and starting with 1 molar aluminum 3+. Now, to figure out which is the reduction process and which is oxidation, we can look at our equation here. Aluminum is being stripped of electrons. That's our oxidation, right? So aluminum is being stripped here, so because it's becoming positive. So aluminum is my oxidation, and then my reduction is, or my manganese being reduced to the metal. So if we looked up those values, this is tricky because we get negative numbers for both. So negative 1.66 and negative 1.18 volts for each of those. So volts. Now, if we were to try and add these together, we know we need to reverse our oxidation, right? So negative 1.18 volts. We reverse the oxidation, make that a positive 1.66 volts. If we were to add these together, we actually do get a positive cell potential, 0.48 volts. And I believe I got those values from the table. Let me double check. So the aluminum, we're looking for aluminum 3 plus negative 1.66, and then the other one was the manganese 2 plus to manganese negative 1.18. Yep, so both those are there if you were wondering where they came from. Okay, so now that we have our E cell, this is going to be our basis that we frame everything around, right? So we're asking to predict whether E cell will be larger or smaller than our standard E cell. Remember that E naught is our standard. If we're looking at A, we're given two new concentrations, 1.0 molar for my manganese, so this is new, N for new, and then 2.0 molar for my aluminum. So what's happening here? My scale is being tipped a little bit. We're increasing the amount of aluminum on the product side. So where is it going to shift? The reaction will shift back to the left, right? We're going to favor the reverse reaction. We know that in the forward direction, we have a positive cell voltage. So if we go in the reverse direction, our E cell is going to get smaller. So reverse leads to smaller voltage, right? Smaller voltage, and therefore smaller E cell. Oop. Not standard, just regular E cell, smaller E cell. Since we have a smaller E cell, we want to compare that to our original. In this case, it will be less than. So it will be less than our E standard cell, our E naught. Let's look at the next one. So the next one, this time we're increasing our product side and leaving our reactant side alone. Where is it going to shift? It's right to the product side. If we're shifting to the product side, then our cell potential will increase, since we are favoring the forward reaction. If our cell potential increases, then E cell will be greater, right? Again, we're comparing E cell to E naught cell. So in B, it will be greater than, because we've increased the concentration of reactants. It's going to shift to the right. We're going to have a greater voltage as a result. Okay. Now, I put this on here again because there's a way we can look at this quantitatively, right? We can actually calculate this quantitatively, okay? And that's using the Nernst equation. So I'll go back to that question in a second. The Nernst equation, it's the E of our cell, so let's say E cell, and then E naught cell, right? So it's the energy produced by the reaction. Our E cell is minus RT. R is your gas constant. In this case, they like to use 8.315. Some places have 8.314. Some places just say 8.31. 8.31 is a pretty safe bet. 8.31 joules per mole Kelvin. Our temperature is in Kelvin. We got to make sure of that. They have N, which is your moles of electrons from the balance equation, and then F, which is Faraday's constant. And then they have the natural log of Q. It's been a while since we've seen Q. We looked at Q when we were looking at equilibrium last year. We looked at it briefly with our K values. A refresher for you, Q is the products. Remember, just like K, if we're looking at K, K is the products over the reactants, right? Our equilibrium constant is just that ratio, products over reactants. But the key here is at equilibrium, so at EQ. With Q, it's just at any point during that reaction, so initial concentrations is popular with this one, so we won't have our initial concentrations here. So initial or the new concentrations. So in the case that we have, we know our initial concentrations at standard conditions are 1 and 1, but now with Q, we'd plug in what it would be if the concentrations were changed. So here we have our reaction. First, let's get to that practice with our Q. We gotta write just our Q expression. So remember, when we write our Q expression, we said products over reactants. We only include the things that are ions in this situation. So here we've got aluminum 3+, and we square it. Why do we square it? That coefficient there. Remember, we keep things proportional due to the coefficients. And then our reactant, manganese 2+, and we also cube that one because of the coefficient. Remember, we don't include solids in our reaction quotient. So we know our original E cell, that was the 0.48 volts, calculated that last time. If we were to run through this, we've got E is equal to E naught minus 0.0592 over N, which is our number of electrons, and then log of Q. Okay, so we could plug those things in. If we go back to our half reactions, we would actually have to go through and balance this if we were going to do it quantitatively before we just reversed. But if we're looking at our half reactions, we know that aluminum and then Al 3+ plus 3 electrons, and then we have our manganese 2+ and plus 2 electrons, and we get our Mn. We would know that if we were to balance these, we have to multiply them by 2 and 3. We end up getting 6 electrons. The other way you can do that, if you're looking for a shortcut, if it's already a balanced equation, we've got our coefficient times our charge, and then we can figure out the opposite of that is the number of electrons, right? 2 times 3 is 6. We have 6 electrons in this reaction here. So if we were to do this quantitatively, now we can plug that in. So we know that N will equal 6 moles of electrons per mole of reaction. Mole reaction, Rxn is reaction. All right, so we can figure out our Q, we'll plug that in. Let's do A first, let's look at A. So A, we've got 2.0 molar squared over 1.0 molar cubed. 1 cubed is still 1, 2 squared is 4. So we end up getting Q is equal to 4. Let's plug in our numbers. We've got 0.48 volts, which is also the same as joules per coulomb, minus 0.0592 over 6 moles of electrons, and then times the log of Q in this case. Log of Q is now 4. All right. So if we are to put this in our calculator, so you got 0.48. Let's make sure it's on. 0.48 minus, and I'm going to put a bunch of parentheses here. So 0.0592 divided by 6, close parentheses, times log of 4, close parentheses, and then close parentheses again. I end up getting 0.474, so 0.47. This is equal to 0.47 volts, and if you look at that, 0.47 volts is less than 0.48 volts, not by much, but it is. And if we go back to what we said over here, we said A was less than, so mathematically we did confirm it. You can use that to double check. So if you are a qualitative not math person and you're qualitative, you can go through and think about it qualitatively. If you are a math person quantitatively, you should be good to go. So just a couple of things, notes on the Nernst equation and our equilibrium constant in G. It's really important to know that as your E of your cell, your voltage declines. Think about what that means. If our voltage is declining, that means we're running out of power, right? Think about a battery. What do batteries do? Eventually, batteries die, right? So as the E declines, all of your reactants are being converted to products. Eventually, there's not going to be any more energy. It's going to reach zero. You're not going to have any potential left. When you're at zero potential, we've reached equilibrium. So essentially, when your battery dies, it's just reached equilibrium, right? So at equilibrium, we know a couple of things. We know that Q is equal to K. Your reaction quotient is equal to K. That just means that the products are equal to the rate of the products forming is equal to the rate of the reactants forming. So other equilibrium notes, when K is greater than 1, the products are favored. When K is less than 1, the reactants are favored. So what's nice is we actually have another version of the delta G equation where we can find K. Before we had delta G equals negative NFE, and we're actually going to use both of these in sync today. Renee McCormick had a really great way for remembering this delta G. She said rat link. It's kind of like rat link, which is weird. So rat link is a way you can remember negative RT natural log of K. Now, since we have negative NFE, and that's equal to delta G, we also know that this is a relationship we're going to have to explore. We could set these equal to each other at some point. Negative RT natural log of K. And obviously, we can get rid of those minus signs, negative signs, because they're on both sides. So at some point, we will have to solve NFE equals RT natural log of K. This is definitely one you'll see on your free response questions. Some of you may have figured it out already. Some of you may still be struggling. That could connect the pieces there. So we're determining the electron flow. And we want to designate the anode and cathode for the cell represented here. Okay. So the tricky part about this one, we've got the same anode and same cathode, but they're different concentrations. So this one we really have to think about what's happening, right? If we've got 0.1 molar on one side and 0.1 molar on the other side, we want to think about what is happening. Which way is it going to shift? Well, the right side is a larger concentration, so the desire is to shift to the left, right? And as we shift to the left, we are decreasing the concentration of Fe2 plus on the right. So, right, if we're shifting to the left, Fe2 plus on the right will go down in concentration. So I'm going to say concentration down. Okay, what does that mean? Well, that means the concentration in my solution here is decreasing. Where can it go? The only place it can go is onto the cathode, right? Things will start plating out on here. So if my concentration is decreasing, it's going to plate out. I know the right side of this is my cathode for that reason. And therefore, the smaller concentration side will be my anode, all right? And we know it flows from anode to cathode, so even though the reaction is moving to the left, the electrons are still going to flow from left to right, right? Because in the long run, we are decreasing the concentration of Fe2 plus. We're decreasing Fe2 plus. If Fe2 plus is going down, that means Fe is going up, which means we have reduction, right? And if we have reduction, then we're going to need electrons to reduce us, right? We got to add electrons to reduce us, right? Reduction is gain. So that one we can just figure out qualitatively from that. So therefore, keep in mind that as we add here, my cathode size goes up as well, right? And then the anode size goes down. Anode size is down, right? Because they have to get the electrons from somewhere. It's stripping it from the Fe2 plus, and we get our battery, okay? Okay, this one is the big one. This is the fun one with our Nernst equation. There's a lot we have to do with this problem. So first things first, it says determine the standard E, our E naught for our cell, and our E cell. So the E cell, the E naught cell is the easy part, right? We just have to figure out which one of these is oxidation, which one's reduction. Remember, if we want this to be a spontaneous cell, we need to have the most positive number possible. So here, the only way we can have the most positive number is if we reverse, I just write reverse, we reverse our zinc. If we reverse this one, that means it's our oxidation, and we're keeping the original one as our keeping the original one as our reduction. So as a result, the E becomes positive here, and we get zinc and zinc 2 plus and 2 electrons. Okay. So clearly, this reaction only has 1 electron. The one on the bottom has 2. We would have to multiply this by 2. I'm not going to balance this entire thing. It's actually, well, it is necessary. I am going to balance this entire thing. Because when we get to the E cell, we need our reaction quotient, right? So in order to write a reaction quotient, we do have to multiply this whole thing. We get 2VO2 plus 4H plus 2 electrons, and we get 2VO2 plus and 2 waters, okay? When we do that, our E naught still stays the same. That is 1 volt. We add those together. Electrons cancel, and I get my balanced reaction. I get 1.76 volts as my standard potential to start with. And then my balance equation, lordy, this one's long. I'm going to write it down here. Zinc plus 2 VO2 plus 4H plus, and we get zinc 2 plus 2 VO2 plus and 2 waters. Okay. All right, so that was the easy part. Now we need to figure out our reaction quotient. With our reaction quotient, I have to remind you that solids do not go in our reaction quotient. It's only things that are aqueous. And water is a pure liquid, so that also does not go in our reaction quotient. So if we were to write our Q would be products. So we've got zinc. I'll write that a little bit neater here. We've got zinc 2 plus, and then VO2 plus, and that is squared. Why is it squared? Coefficient. And then our reactants, VO2 with a 1 plus charge, also squared, and then H plus with a 4th power. Okay, so that is our Q. Now we can plug everything in that we need to plug in, right? So nice thing is we're told it's at 25 degrees, so we can use E is equal to E naught minus 0.0592 over N and log of Q, right? Okay, so here's the fun part, plugging it all in. So we've got 1.76 volts minus 0.0592 over 2 moles of electrons that are being transferred. And then the log of Q Now I have to plug in my concentrations, and this is where it gets crazy. So I've got VO2 plus, which is 1.0 times 10 to the negative second molar squared, and 1.0 times 10 to the negative first molar. And then I'm dividing that by 2.0 molar squared and 0.50 to the fourth power. All right, putting that whole thing in parentheses. So let's do some order of operations. Calculator time. Okay. So in parentheses, first thing I want my 0.0592 divided by 2, close parentheses. It's going to be times the log, and I'm going to do separate parentheses for the top. So I need actually a third one here. So we've got the top 1.0 e negative 2 to the second power, close parenthesis. All right, actually I'm going to need even another one. So think about parentheses. This is a parenthesis crazy thing. If we need help putting this in the calculator, we'll work through that, okay? And this is times parentheses 1.0 e to the negative first, close parentheses, that one's fine. And then we've got to close our parentheses again one more time. And then we're dividing by our 2.0 squared. 2.0 squared, I should have put the squared in here. Do that, that's easy. 2.0 squared, and then times, it's 2.0 squared times 0.5 raised to the fourth power. Okay, close parentheses, boom. So I get a negative 0.13. The hardest part, I think, is putting this in the calculator. Negative 0.13 volts. So when I go back, I end up getting 1.76 minus a negative 0.13. Remember, if we subtract a negative minus a negative, it's the same as plus a positive. We end up getting 1.89 volts as our E of our cell with those new concentrations. So we found everything. We found E cell and we found our E standard. That's a doozy of a problem. It's actually pretty cool. We just got to keep track of this madness here when we put it in a calculator. Okay. All right, one more and then we'll be done. All right. So this one, nice thing is they give you the half reactions. They want you to balance, calculate E and K. So before, remember I said we had that delta G equals NFE, negative NFE, and that we have delta G equal a negative rat link. We're going to have to put those together for this problem, and that's where it gets fun. So to balance, all right, we see that this is our reactant. Here it's on the product side. This is our oxidation. We're going to have to reverse this. Reverse this. This is the reduction because those are on the right side. Boom. When we reverse it, this becomes positive. And so we end up getting 0.67 volts as our E cell. If we were to balance, we also need to multiply this by 2. So not only that, but we got to multiply by 2 and reverse it. So we've got S4O6. Actually, I don't even do that part yet. I'm just going to switch it. So Cr2 plus, 2Cr2 plus, and then 2Cr3 plus, and then plus 2E minus. Okay. Now we know we need to add these together. When we add these together, my electrons cancel, you get S4O6 2 minus plus Cr2 plus, 2Cr2 plus, I'm sorry. 2Cr2 plus, and 2Cr3 plus, and 2S2O3 2 minus. Okay. So, a couple of things we definitely need to know. Our number of electrons here. In this case, it is 2 moles. Now, I know your inclination is to jump to reaction quotient because we just balanced this equation. We have this. We know about our Nernst equation, how the E cell is equal to E naught minus all that mumbo jumbo. But read carefully, what do we not have? We aren't given any concentrations. So if we're not given concentrations, that Nernst equation is out the window. So this is our only option up here. So even though we balanced it, I'm going to say bye-bye. Sorry for showing you that extra work. We just got to be careful when we read, right? So we know we have 2 moles of electrons. I know I had to reverse that one. We have our E cell. Let's calculate. Let's set these equal. Negative N F E equal to negative RT natural log of K. Okay? And this is a standard cell. We're told the temperature, so we can assume what T is. We can assume T is 298 K. So let's plug in our numbers and then solve. Let's actually rearrange. If we want to get natural log of K by itself, negative RT on both sides. This would become positive and positive. Those cancel. We end up getting natural log of K equal to NFE over RT. Okay, remember this isn't the 0.083 or 0.0821 R value, it's the 8.31. So when we plug in, we can get natural log of K is equal to my 2 moles of electrons, 2 moles of E, times Faraday's constant. I'm going to use the real value because I think it's fun. Coulombs per mole of electron times my E value, which is 0.67 joules per coulomb. And then we're going to look at RT, and this is 8.31 joules per mole K. And then we've got times 298 K. So in the long run, all of my units are going to cancel out. Remember that K has no units, right? It's just a product, the ratio of products over the reactants, right? A large K means where products favored, a small K means where reactants favored, okay? So let's put this all in our calculator. This one's a lot easier. So we got turn on a calculator. So let's do the top first. So 2 times 96485 times 0.67, close parentheses, divided by 8.314 times 298. And we get 52.18. Okay, so I'm going to write that down. 52.18, right? But that is not our K value, that is not our answer. We have to remember that natural log of K is equal to 52.18. The only way we can get rid of our natural log is if we raise both to the E power, right? E raised to the natural log of K would cause the natural log to cancel, and we would end up getting our answer of K is equal to E to the 52.818. Let's see what that is. So if you don't believe me, here, let's just test it out real quick. You forgot your logarithms. So E raised to, let's just use an easy one. E is the natural log of, say, 5, right? E raised to the natural log of 5, boom, cancels out. It is 5. So we're going to do that same logic. We said E is the natural log of K, we get K, and we said that that was equal to, sorry, I got to go back. What was my number again? 52.184. So E raised to just going to say second answer, so I put that whole thing in there. I get 4.6 times 10 to the 22nd. Wow. So 4.6 times 10 to the 22nd. This is my K value. And now let's evaluate it. That's a pretty large K value. What does it mean? Hopefully you said a large K value means the products are extremely favored. This is a great thing. That means our battery is going to run. It is spontaneous. Okay. And that's it. Thank you very much.